So my name is Ritchie Vink, I'm the author of Polars.
I have a background in machine learning and software development.
Yes.
Polars is
3 years old now, and my first talks always were like, what is Polars? And how does it work? What is the API? And I wanted to do it a bit differently this time. So it does work? Okay. Then I'm gonna talk a little bit louder. Can everybody hear me?
Yeah.
Cool. Okay. I made an assumption that Polars now is at least known by people, and some people have used it. So I want to check if my assumption is correct. Who knows Polars? Right. So it's about 50-50. Who has used it? 10%? Is that generous? Okay, so my assumptions are not entirely correct, but I think the talk will still be useful because learning how to use Polars, you don't need me for that. You can just go on the internet and go to the documentation. I think it's more interesting to go into the nuts and bolts of Polars a little bit. So today I want to talk a bit about what is Polars in 5 minutes, a very short introduction, and then I want to walk through a query and see what actually happens, what kind of decision Polars makes. So Polars in 5 minutes, the elevator pitch. Polars is a data frame library which respects 50 years or so of database research. And I would argue that this wasn't the case with earlier data frame implementations, except for PySpark. So things we have, for instance, lazy evaluation. Lazy evaluation means that if you write your query, we won't execute it immediately, but we will see if we can do things smarter. We will optimize your query, and for instance, if I ask for a coffee and you go straight away, and then you come back and I said, I also wanted sugar, you have to go again, so it would be wasteful. If you be a bit lazy, more laid back, you can get the whole query and do things a bit smarter. We minimize materializations. So for instance, if you ask if you load a file and you only need the first 100 rows, it would be wasteful to load the whole file first and then explode RAM. Materializations are very expensive. We have data types that are constructed to amortize cost of access and allocation cost. This is actually done by Arrow. We follow the Arrow specification for most of our data types. And with amortizing access, I for instance mean with string data, opposite to how pandas did this in the past, where they stored a string as a heap allocated buffer. If you do this for every string, you need to go to the heap for every string you have in your column. And we have a single heap allocated buffer for the whole column. It's written in a low-level language, which I think is really important for a query engine. You want to have full control of performance, you want to have full control over memory, but also over threading and critical paths. It is designed for effective parallelism, and I want to understate effective parallelism. There's also a lot of parallelism that isn't effective. If you, for instance, use multiprocessing, going to another process is really expensive. You need to serialize data, you need to copy data. But also, even if you stay between threads, parallelism cannot be effective. If you, for instance, have a lot of mutexes and you lock everything and only one thread at a time can access that data, it's also not really effective. So we try to have lock-free parallelism as much as possible, and communication with threads is really reduced to a minimum. And it's being designed for out-of-core processing. Out-of-core processing means we can process data sets that are larger than our available RAM size. We can, for instance, do this by processing data in batches, but also some operations need all data, but they don't need it all at once. So we can also spill to disk again in a smart way, and doing that asynchronously and making sure we can still do compute while we're spilling to disk, for instance. And we have really tight integration with I/O. So we have written most of our I/O readers ourselves, and all our optimizations are being pushed down into our I/O. And Polars is really modular. It's written in Rust as a data frame library, a query engine, which can actually be exposed to any frontend. I think the most famous frontend is Python. It's our de facto implementation, but we also have a data frame frontend in Node.js, We have one in R, we have one in Ruby. You can compile it to WebAssembly. We have a SQL front end. And also, a fun thing is, for instance, there is a programming language called Elixir, which also wanted a data frame library. And they just took the Rust data frame library and bootstrapped that into their own Explorer data frame library. So it's actually super modular, and if you build a new language and you need a new data frame library, but you don't want to adhere to the Polars API, you can still take the whole code and build upon that. And it's also used in the new shell data frame API. New shell is a shell like Bash is a shell. The benefit of all these front ends is that all edge cases, but also all contributions flow back to a single implementation. If we make Polars the core better, we make it better for all these front ends. So yeah, there's a lot of benefits, like doing one thing very well for all these front ends. Yeah, and yeah, it's the elevated pitch, so I have to say it. Polars is really fast. It's one of the fastest data frame implementations on a single node. Maybe it's the fastest. I would probably dare to say that. And it's very fast because of these reasons. One of the major reasons is the amount of effort we took in to really write the algorithms very cache efficient, really think about what we're doing. Its design, we have designed it for parallelism from the ground up, and we've started from scratch, and took like 2 years before we were on a usable level. Like we didn't take something from the shelf. Yeah, we really designed it from scratch. We have a query optimizer, which can save a lot of work. It can actually prove that we don't have to do certain kinds of work, and the best work is work you don't have to do, so that can save a lot of time. Also a lot of memory. It's written in Rust, so it's as fast as C and C++. It's got a columnar design. The columnar design, so if we, for instance, look at databases or Spark, those have a row-based orientation, memory orientation, but this, it's really hard to have SIMD factorization on row-based memory formats, and it's not really cache-friendly, and you also have a lot of padding bytes to make your different data types on a single row fit together. So there's a lot of bytes wasted, which are bytes also on the cache, which means you have less usable values on the cache. So vectorized databases turn out to be the fastest databases for OLAP, and we follow that design. And these are benchmarks that show the performance of Polars. This is a benchmark run by ourselves. It's the TPCH benchmark. The TPCH benchmark is a benchmark written for databases, mostly for SQL, but we translated the SQL queries to data frames as well. So to the left you see Polars. This is the Polars part, this is WB, this is Pandas 2.0, 2.01, and this is DAS. And we also have VEX, but we couldn't finish our queries. But you can see WB and Polars are on a whole other league, right? Query 1, we still have to optimize. I know it hits a part where we didn't have the time to. It hits a part in the new query engine, which we haven't optimized as much yet, so we know we're not on the limit there. But the other queries are representable, and you can see we actually beat DuckDB for in-memory queries most of the time. Yeah, so Polars is a super fast query engine on a single node. Here's another benchmark. This is a benchmark run by DuckDB. It runs the latest DuckDB, but not the latest Polars, so a few of our optimizations are not in there. What's interesting here is that you also see other data frame implementations like Spark, also Pandas 2.0, and also Arrow. And Arrow is interesting because this is where Pandas will go in the future. This is the C++ Arrow backend. Polars has their own implementation of a group by, so we don't use Arrow compute, we only use the Arrow memory format. But every algorithm is written by ourselves. So even though we both use Arrow as a memory specification, you cannot say that the compute performance will be the same. Yeah, so very good benchmark. This benchmark is not run by us. This benchmark is run by DuckDB. Yeah, okay, that was the elevator pitch. Let's go through a query. So this is a query in Polars. It takes a query from the TPCH dataset, and we adapted a little bit just to show some interesting features of the optimizer. The query doesn't make much sense in a business level, I think, just shows some data. So we scan a bouquet file, we filter where a ship date is lower than a certain date, and then we select the join keys and some expressions. What those expressions are, I will show in a bit. And then we join that query plan with itself. And finally, we sort and we take the last rows. So first, I want to go into the expressions. So here you see the expressions from this query. These expressions are quite simple. You sum, you take column A, you multiply times 1 minus column B, and you sum that result. I didn't come up with this. This is the query from the PCH question. But what I want to show more is what we do with the expression. So Polars expression engine is actually really powerful. You can combine expressions indefinitely, and they are super fast. And what we do when we read an expression, we translate it in an expression tree. So you get a tree something like this. So here you would have 5 plus 9 times 2 plus 3. That would be an expression, and we would evaluate from the bottom up, right? But we wouldn't run this as is. We wouldn't run this naively. So the first thing we do when we get such an expression tree is look for errors. And we actually do this on the whole query. The first thing we do is, does the schema make sense? Do you select columns that don't exist, and we throw an error immediately? Because my experience as a data engineer was that you could get errors 20 minutes in your ETL pipeline, and that was no fun. So you want something to fail fast. It should explode in your face, right? You want to know, okay, this is wrong. What happened? So we check the schema before we run the query, and then we do a lot of optimizations. These are not all of them I show here, but some things we do, for instance, is constant folding. So, for instance, if you would have a column and you would add 1, you would need to allocate a new buffer, and then add 1 for every element. Then you're done, and then you add 2. You allocate a new buffer, add 2 for every element. This is very wasteful. If you can prove, you can just do 1 plus 2 first. So 1 plus 2 is 3, and then you only allocate a buffer. This saves an allocation run and 2 passes over the data, or 1 pass over the data. Fused arithmetic. So, for instance, A times B plus C, we do this in one operation. So we allocate once, and we take the 4 columns, and in one allocation, we do this operation. We call that fuse. So you fuse it in a single loop. And if your expressions get more complicated, you can hit more of those fused arithmetic trees. I see, is this clear? I see an expression that, so in a single loop, you do A times B plus C. Instead of doing this first and then this, you do it in a single loop. And in a single application. But we also replace functions. If you see a function, for instance, if you first do a sort and then a head, we actually realize, hey, this could be a top K. The user didn't realize, but we realized it. So we replace this function. And we reuse buffers. For instance, if we have buffer A and it comes from a data frame, we cannot use that buffer because the buffer is still in the data frame. We cannot overwrite that data. But once we multiply it with column B, then we have a new buffer, which doesn't belong to anyone yet. So we can reuse that buffer if we do the next multiplication and the next. So this saves a lot of allocation costs. And it's embarrassingly parallel. So every expression runs in parallel. And we apply word stealing. So if an expression is done, it can take another job on the queue. And by doing this, we're actually able to keep all the threads saturated with useful work most of the time. So it's super satisfying. If you run Polars, a Polars query, and you have htop on open, everything is green. All the threads are yeah, jamming it. So let's take a look at the query. So it translates to a query plan, and here we see a query plan. So you can read it from top down. So we finished with the dot head, right? And that will be the top of the tree. And then we have to sort, then we have to join, and as you can see, the join has two branches, but they are actually from the same subtree, right? Because here we join with ourselves. Q.join QU, right? So we join with ourselves, so those two branches are actually from the same subplan. And there's also some database arithmetic, like pi. Pi means how many columns you have selected, and sigma means means a filter you have applied. So what it shows here is that we selected all of the 17 columns and we applied no filter at the scan, right? But here we see we only use 12 of the 17 columns. So we shouldn't have loaded all of them. Makes sense, right? So the query optimizer realizes this. The first thing we note is that the head is gone. The head node actually has gone into the sort by, and this will not do a naive sort by anymore. This will do a top k node instead. In the join, we see that we only see a single branch here. So the query optimizer realized that those parts of the subtree are the same. And we can actually just load it once and cache the result. And once we're on the second part, we just take that intermediate state. We cache it once and then it can go out of memory. So this will save a very expensive I/O cost. And we have pushed down the selections to the scan, so we don't load all the columns, which means we also don't apply the filter on all the columns, and we actually apply the filter on the scan itself. And this is for K data. K data can often have statistics, so it could even be the case that the statistics show that we don't even need to load certain row groups. This is not always the case, but it can be the case that we don't even need to load data, that statistics can prove that. If we do have to load data, then we apply the filter at the scan level, and it still means we have much less materializations. It's clear, right? And once we have finished optimizing the query, we execute the query. And Polars has two engines for this. We have a default engine, and the default engine is optimized for performance. Completely for performance. And it works completely in memory. And if we run a query, we start top down and we ask every operator, okay, can you give me the result? This operator doesn't have a result yet. So it asks it here, can you give me the result? This one asks it to the right, can you give me the result? And this one actually can create a result and pushes it up. So every operator itself is completely parallel aware. It can define by itself how much parallelism it needs to do, and it can publish the parallel jobs on the work stealing thread pool. But an operator can only publish its work to the next one when it's completely done. So it passes along complete data frames across this boundary. It will not be partial data frames coming across this boundary. So every operator itself is responsible for the full parallelization of that job. But we can execute these two in parallel, for instance. Right? The benefit of having all the data available in a single operator is that they can make ad hoc decisions. They know exactly what kind of data they have. So they can do sampling to explore what kind of cardinality there is and maybe choose for a faster algorithm. Or they can realize, hey, this data is sorted. I can use a sorted fastpath, or can I use this index? So by having this completely in memory, there can be a lot of fastpaths. And I would say we have the query optimizer in the query optimizer itself, but also during runtime ad hoc, just in time. But the downside also is it's in memory. If it doesn't fit into memory, then it doesn't fit. So we have a second engine as well, and this is our streaming engine, and we call it the streaming engine because we stream the data from disk in batches. And here the operators, I have 5 minutes? Yeah. And here the operators are parallel unaware. So what we actually do is we stream the data from this and we push it in pipeline. So what you see here is a join, right? So you see a join, left side, then here's the sink. You call that a sink because it cannot push the operators any further. Then we push this one, and then we can finalize the whole query. So we traverse it from this side out. These green things, this is also green, this is also green, these are actually white, and every thread has a pipeline. So you can, instead of this being a single pipeline, you should imagine that it's a pipeline for every thread, and there's no communication here. You can just push the batches into this pipeline for every thread locally, right? And then the sinks themselves, those need to do communication, and those are parallel aware. For instance, if I want to do a sort, I need to have all data first to understand how I should sort this. So these guys are parallel unaware, and they just pass the data through and apply their operations. So that they can, for instance, do it. If you multiply a column times 2, we can do this in batches, right? I don't need to know what the next batch is to multiply a column times 2. But if I do a sort, I need to know all the data. So these are a bit more complex. These will do parallel aware. Those are parallel aware, so they do some kind of parallelization themselves. But they also spill to disk if needed. So if the goal of this engine is to be able to process any data set size that fits onto the disk. So if this is a blocker, if you want to do, if all the data streams in here, you will run out of memory if you need to sort all the data. So it also needs to spill to disk, but the operators themselves figure out how they do that. This doesn't matter for an end user. It's more like how does it work, right? Yeah, and that's the streaming engine. This engine doesn't work completely on our API yet. So we have it working for joins, for group bys, for sorts. But we don't have it working for window functions yet, for instance. We don't have it working for as-of joins yet. So we don't have our whole API in there, but we're getting further and further, and this is the focus of us for this year. So the goal with Polars is that we can process data sets up till 300 gigabytes on your laptop. Your laptop is super powerful. I've got 16 threads, 16 cores on this machine. I've got 1 terabyte of disk. Yeah, it's got all the hardware available, but we're not using it efficiently enough, in my opinion. And this is actually what I wanted to show with our talk. I haven't touched on the API, but our API is super declarative, which means that our expression, our query optimizer knows exactly what the intent of a user is. And this makes it very suitable to go into a scalable solution, because when you go scalable, you need to know what the user intends, because you need to make those optimizations. You cannot run a query naively, because you need to, it would be too expensive, right? We don't have infinite memory, we don't have infinite RAM or infinite machines, so we need to do this smartly. So we optimize query, we have blazingly fast operators, we don't have a GIL, and what's also interesting is that Spark, for instance, Spark was built in Scala and always was I/O bound, but times have changed, and single machine have got faster and faster, and it turns out that Spark isn't I/O bound anymore for a lot of processes. Currently, Databricks is writing a Photon engine because it's CPU bound now at some processes. So Spark is, they translate just in time to the Photon engine because it can save work for them. And Polars already is here, right? Polars already has all these fast operators and has all this architecture in place to build the. But what Polars still lacks is the distributed orchestration. So that's what the second thing is we want to focus on. Some last words. I want to talk about the roadmap. I already said a bit. We really want to focus on scaling. First on scaling on a single machine, and then we want to scale to distributed as well. I don't like that there are two APIs, like small data is written in pandas, big data is in Spark, so you always need to translate. And I don't think that should be necessary. You should be able to do this in a single API. If you write polars for small data, we should be able to run this on big data. That's where we want to go. And we want to focus on vector data as well. You see the last DB talk? I promised. That's the new data type we want to add to polars. And another new thing is that Polars, the company, I started a company. Until now, we're 3 years old, not even there. We're almost 3 years old. And the only person who did this part-time, full-time was myself, and the rest is open source community. Super grateful for that. But yeah, from now on, we can also pay people and have a professional development team on this. So I think the glory days are in the future. This was all still hacking on my room, on my attic, with open source help. And I want to thank everybody for the adoption because, we see a lot of data tools and Polars adoption has been great. It's, thank you. Do we have time for questions? Oh, cool. Yes.
Well, so I've been a huge fan of Polars since I started using it more or less 1 year ago. And I wanted to ask you, like, how has been your experience? I suppose that you were a Python person before, and then you started learning Rust. Maybe that was not the case. Like, how it's been writing a library that has both Python and Rust on it?
Does everybody hear the question? So the question is, how has it been writing a library that, from a Python point of view, or as a Python developer? I would say, when I started Polars, I was already playing with Rust and doing some side projects in Rust. And I actually didn't start Polars because I wanted a better world and I saw something wrong with the world and this is how I'm going to solve it. It was actually, I just started a side project in Rust because I was interested about the Arrow project and I wanted to do something with Rust and with Arrow. And I needed to join 2 CSV tables, which I had on disk and I couldn't in Rust. So it started like that, but when I started Polars, I wasn't that advanced in Rust as I am today. And we made design mistakes in the beginning. Inevitably, you make design mistakes. But what I learned about Rust is the compiler is so strict, it doesn't let you compile if the types are incorrect. That we were able to do refactors that were like throwing everything, doing everything differently, and you would have a bad 4 days, right? Chugging through compiler errors, drinking a lot of coffee. But the magical thing is, once you're at the end of that tunnel, it works. And this is something I would never dare in Python, because if the code base is super big, in Python it doesn't complain and it will fail at runtime. And I think having large repos, large code bases in Rust is way more maintained. Yeah. But to give Python credit, using Rust or using Python is much more fun to use. I like using Polars much more in Python than I like in Rust because of compile times, strictness. That's not really fun if you're doing data exploration. Yeah.